Hello, in this video I'm gonna be finding the other roots of the minimal polynomial of this element over the rational numbers. First, we start by noting that these two fields are equal. This follows the same way that it did in a previous video that I made with similar numbers. In that video I showed that this was a subfield of this, well that's trivial, but mainly I showed that this was a subfield of this one. And that follows by showing that the generators are in the other field. So to do that, you write, for example, the square root of 6 as a rational function in this element. So now that we have this representation, it's easy to see that this is not a normal field because the minimal polynomial for the cube root of 5 does not split. That means that not all of the roots are in the field. This follows because the other roots are complex numbers, and this is a real number, this is a real number, so adjoining real numbers to the rational gives you a subfield of the real numbers. But this can be easily remedied by adding the cube root of unity, because the other roots of the minimal polynomial of the cube root of 5 are omega cube root of 5 and omega squared cube root of 5. Omega has degree 2 over the rational numbers because its minimal polynomial divides x cubed minus 1, and x cubed minus 1 is reducible. This extension is of degree 12 over q, and that can be easily seen from here. This is a degree extension, this has degree extension 2, this has degree 3, this has degree 2, so it's 12 in total. And well, the main thing is that these two are co-prime and that this is complex, so it's there's a small argument to be made here, but you can probably do it yourself. So since it's a separable normal extension, it's Galois, so we have 12 automorphisms that fix Q. So 12 Q automorphisms. And we can see that these automorphisms are just combinations of automorphisms moving around the roots of these two polynomials. So, for example, square root of 6 can be mapped to square root of 6 or to negative square root of 6. Cube root of 5 can be mapped to any of these three elements. Since the Galois group acts transitively on the roots of the minimal polynomial, we have all of the possibilities. So one other example of a root of the minimal polynomial of this would be by moving the cube root of 5 to omega cube root of 5. So this is another root. And another example would be, for example, 3 square root of 6 plus 3 cube root of 5, so on. So we have 12 other possible roots.